Imagine shrinking your tools down not just to the atomic level or even inside the nucleus of an atom, but even deeper, to the level of quarks and gluons, the very things that make up protons and neutrons. This is the ambition of Atto Technology, the theoretical science of manipulating matter at the atometer scale, 1018 meters. That is 1,000 times smaller than the nucleus of an atom. If nanotechnology is like building with Lego bricks and femtechnology is like reshaping the clay inside those bricks, AttoTechnology would be editing the molecules of the clay itself, the quarks and gluons governed by quantum chromodynamics. Though you might ask, is such manipulation even possible? As of today, the answer is no, but not because it violates the laws of physics. In fact, QCD is one of the best tested theories in science. The problem is that quarks cannot be isolated. They are permanently confined inside larger particles, and manipulating them requires astronomical amounts of energy, far beyond anything available on Earth. Our best particle accelerators like CERN's LHC are still millions of times too weak to control quarks with precision. But the theoretical possibilities are breathtaking. Imagine for a moment that we could control quarks and gluons. What could we do? One fascinating idea is the creation of exotic baryons, particles made of unusual combinations of quarks, like strange quarks or charm quarks. This could lead to the production of strange matter, a hypothetical super-dense substance that could remain stable under extreme conditions. It might be harder than anything in the known universe, useful for spacecraft shielding, energy storage, or even new forms of computing. Let us pause for a moment and ask, how could such matter transform energy systems? Today's nuclear power relies on fission and hopefully soon fusion, processes that harness energy from protons and neutrons. AttoTechnology could go much further, tapping into energy stored in gluon fields and quark configurations. If we could stabilize these exotic states, they might act as ultra-compact fuel or even allow energy extraction from the vacuum itself, based on quantum field effects similar to the Casimir force, though such ideas remain highly speculative. And what about computing? We often hear about quantum computers using qubits based on electrons or photons, but Atto Technology could, in theory, allow us to build quark-based computing elements. These would operate on color charge interactions, the QCD equivalent of electric charge. Gates could be made from gluon field transitions. Though this sounds like deep science fiction, it's rooted in real physics. It would be like moving from abacuses to transistors, then jumping directly to QCD logic gates, operating in dimensions we can barely conceptualize. Could Atto Technology even impact biotechnology? Surprisingly, yes, though not in the way we know it today. While biological molecules are far larger than quarks, particles engineered at the attoscale might serve as probes or catalysts for influencing nuclear decay processes within living cells. In some distant future, fundamental particle medicine could emerge, using attoscale particles to target disease at the subatomic level, or even stabilize rare isotopes that interact with biomolecules in entirely new ways. But with such power comes extreme danger. One of the scariest possibilities is the creation of strangelets, hypothetical particles that, if stable, could convert all nearby normal matter into more strange matter. While purely theoretical, some scientists worried about this risk when the LHC was first switched on. Even though those fears were overblown, they highlight a real concern. Should we manipulate the very code of the universe without fully understanding the consequences? So where are we now? The reality is that Atto Technology is far beyond our current technological horizon. Even the most powerful machines on Earth cannot reach the required energy scales. Theoretical physics gives us the blueprint, but engineering at the QCD level remains science fiction for now. Some speculate that within the next 200 years, advances in quantum computing, attosecond laser physics, or even new states of matter might offer indirect ways to influence the attoscale, but nothing is certain. In the meantime, we continue to push the limits of what we can simulate. As quantum computers become more powerful, they may help us model QCD systems in real time and eventually guide us toward the first indirect forms of attoscale control. Think of it as a slow journey, like early humans learning to harness fire. We understand the theory, we see the potential, but the tools are still generations away. So, will we ever enter the era of AttoTechnology? If we do, it could mark the moment when humans gain not just control over matter, but over the fabric of physical reality itself. It is the most radical idea science has ever entertained. Rewriting the universe, one quark at a time. Technology operates at the atometer scale, which is 3 orders of magnitude smaller than nuclear dimensions, entering the regime of quarks and gluons, the constituents of protons and neutrons. The interactions at this level are governed by quantum chromodynamics, QCD, the theory describing the strong force and color charge. Unlike in nuclear or atomic systems, quarks cannot be isolated due to a phenomenon called confinement, which keeps them permanently bound. Any manipulation at this scale would require reconfiguring color charge dynamics and controlling gluon-mediated interactions inside hadrons. Technologies capable of such manipulation must overcome unprecedented energy and stability constraints while respecting the constraints of QCD. A controlled configuration of 3 quarks UUS up strange could form a stable exotic baryon with new properties if nanotechnology is arranging bricks and femtechnology is adjusting cement molecules. AttoTechnology is reprogramming the atomic code inside the cement itself. AttoTechnology aims to rewrite matter from the inside out by altering the internal quark structure of hadrons transcending the periodic table. This could enable the creation of exotic hadrons such as tetraquarks, pentaquarks, or theoretically stable forms of strange matter. By manipulating color confinement and binding energies, one could build new types of matter with ultra-high density, stability, or magnetic properties. These engineered forms could behave unlike any natural element, resistant to radiation, decay, or extreme temperature. Such designs may bypass the standard model limits, pushing into post-standard physics. A new form of matter engineered at the Atto scale might remain stable even inside a neutron star environment. Like designing a new alphabet by changing the shape of the ink molecules inside each letter. QCD contains immense latent energy. 99% of the mass of matter arises not from quarks, but from gluon field dynamics. AttoTechnology could allow us to store and release energy by engineering the QCD potential wells inside hadrons, enabling power densities vastly beyond fission or fusion. Controlled reconfiguration of quark states could provide stable energy release or even tap into the QCD vacuum energy under Casimir-like constraints. Hypothetically, this could lead to room temperature ultra-dense energy systems. However, any practical application would require precise field control at exascale energy densities. A QCD mixtured particle could release more energy than a nuclear warhead from a grain of material with perfect stability, like charging a battery not with electrons, but by twisting space inside the battery's atoms. AttoTechnology could enable computation using quark states as logic elements instead of electrons or photons. Qubits based on color charge, spin parity, or gluon coherence may represent ultra-stable information units. These hypothetical strong force logic gates could outperform quantum computers by operating within femtoseconds and being inherently protected from electromagnetic interference. The circuits would operate not with wires but with controlled gluon tunnels, forming a speculative QCD-based architecture. This would constitute a shift from QED-based systems to a computation regime native to the strong interaction. A baryon with engineered spin-up and color state combinations could act as a self-contained logic processor. It's like computing not with electrical currents, but with miniature nuclear fireworks encoded in each gate. Though biology exists many orders of magnitude above the Atto scale, future interactions between Atto-designed particles and biological matter might create new medical tools. Quark-measured particles could target nuclei within biomolecules or alter radioactive decay for therapy. Attobots, particles with engineered nuclear spin, might be used to probe or control cellular environments indirectly. Isotopic stabilization at this level could also enable long-lived, ultra-precise tracers or therapeutic agents. This would not resemble genetic engineering, but interaction between living systems and QCD-structured particles. A medically safe strangelet could target cancerous nuclei and decay with surgical precision, destroying only affected cells, like designing a scalpel so small it cuts inside the nucleus of a cell without touching the rest of the body. By engineering matter with quark-level structure, AttoTechnology could enable mass energy control mechanisms for future propulsion. Negative mass configurations or controlled gluon transitions might produce exotic thrust mechanisms akin to Alcubierre-style drives. Defense applications might include gluon-based shielding, nuclear stability amplifiers, or directed energy pulses originating from controlled quark phase transition. The ability to reshape baryonic matter dynamically could enable weapon systems orders of magnitude more powerful, or shields impervious to existing force types. These ideas are mathematically grounded, but still speculative due to energy requirements. A propulsion system using engineered decay of ultra-dense atom matter could deliver impulse without ejecting mass, like building a spaceship engine that moves by editing its own mass distribution in real time. AttoTechnology is completely beyond today's experimental reach. Manipulating quarks individually is impossible due to confinement, and the required energies, 106 to 107 DeV, exceed even the most powerful particle accelerators. Instruments with atometer spatial resolution and yoctosecond temporal resolution do not exist. Additionally, the uncertainty principle and gluon field instability make any stable manipulation extremely delicate. Even modeling these systems requires petabyte-scale lattice QCD computations, often impractical in real time. The LHC, our most powerful collider, cannot isolate or move individual quarks without destroying the surrounding nucleon. Like trying to adjust a piano string while the piano is falling from space and exploding simultaneously. Progress toward Atto Technology will likely follow breakthroughs in femtechnology, high-energy quantum computing, and QCD modeling. Between 20502 100 femtoscale material control may mature. After 2100, QCD simulation and vacuum engineering might enter experimental physics. Attosecond laser fields, quantum-enhanced lattice solvers, and hypothetical QCD field concentrators could lay the foundation for primitive attosecond laser fields concentrators could lay the foundation for primitive attopeculation. Long-term progress depends on whether we can extend or modify the standard model, possibly through discovery of new stable particles. The final enabler may be the development of quantum intelligence capable of simulating and controlling quark behavior in real time. In 2150, a femtech-driven lattice QCD computer might simulate gluon behavior fast enough to begin localized attoscale engineering. Like learning to sculpt in pure light, where every movement changes the fabric of reality, technology challenges the very notion of what matter is, redefining it as programmable fields of confined quantum energy. The ability to control the strong force could unleash transformative or catastrophic powers, including metastable matter that reshapes ordinary atoms. Philosophically, it blurs the line between physics and metaphysics. If you can rewrite the structure of space-time's building blocks, are you creating a new universe? Ethically, the technology raises questions about control, weaponization, and irreversible planetary scale consequences. If realized, AttoTechnology could either end civilization or redefine its trajectory forever. A microgram of poorly contained exotic quark matter could theoretically convert the planet's mass into strange matter. Like writing code into the operating system of reality, a typo could crash the universe.